until it records for a few seconds. But it's okay that I wasn't recording because everybody is here and everybody was listening and awake. So that is okay. Let's have a look at the formula here. Unless somebody wants to give it to me now. I know you saw that on the intro slide. That is not it. Nearly though. Okay. I'm sure one of you knows what an analogy is. Yes? Go for it. Explain an analogy. Do you know, Andrew, analogy? Yeah, but give me like a simple, couple of word explanation if you know it.
Idea to explain something.
Not quite. It's missing a key concept. It is used for explaining though. Explaining an idea, like you said. But a key thing about an analogy is that you're comparing two things to help explain. So, to explain the next part, I will go back to mechanics to help explain it. So here is the ground. And here's a particle of mass m. And it is being pulled down with a force mg. And it's at a height of h. And what is the potential energy here? mgh. Okay so far? Now, let's say instead I have a positive particle, and here I have a negative charged plate. And let's say likewise here there's a force. But what's the force here? Between two plates. QE. Yes? QE. And again, let's say the height here above the plate is h. Now, let's just go back here for a second. What does the g represent in this formula? Well, it's a force, isn't it? So F equals ma, but it's also equal to mg. So the a is equal to g here. And what does the m represent? The mass. So the m is something about the particle, and the g is about what? Yeah, the space. Now if you look here, the q is something about the particle. What exactly is it? It's the charge of the particle. And the e is something about the field. So you can kind of see this sort of comparison between the two. So if you were to have a guess, what do you think the potential energy formula is here?
Q, E,
H. Or, as I think it's normally written in books, they use D here for distance, because it could be vertically or it could be horizontally. So I shall use D. Now you notice that I didn't prove this formula. I just drew parallels with the mechanics lesson for a similar situation and concluded that the formula must be this. Now I could prove it. It'll not take too long to prove, but the proof is very similar to the proof in semester 1 for the formula, except instead of writing things like mg, you're writing QE. Yes? You seem so confused or tired or both. Both. Yeah. Anyways, if you do not see my analogy, that's okay. You can just take what you're supposed to learn. This is the formula for potential energy of a charged particle in an electric field.
Wait, so m is equal to q.
No, that makes me so sad that you said that. Because when in an analogy you compare two things, but you're not saying that A is the same as B and C is the same as D.
Yeah, but
it's a comparison.
Yeah, we're taking Q as M.
Yeah. So use the right words. Q is like M, and E is like G. Now that's actually very important. E is like the G here. What does E represent in this story? The electric field strength. So that means the G must represent some kind of field strength as well. Gravitational field strength. And this we will learn more about later in the chapter. Yes?
I just have one
Yes.
confusion.
Yes.
Isn't QED end of proof?
It is. Capital D though. Yeah. Yes. Yeah. Totally different. And I haven't decided on if I want to use a small q or a big Q. I sometimes switch between the two. And if you go back on my videos, you'll notice I first mentioned that 2 years ago. I still haven't decided yet which one I want to use. Okay, can you write that down? So this is the proof of it. Quick spot check question here. What's the units for E? Newtons per coulomb. Q? And D? Now watch this. Coulombs, newtons per coulomb, and D? Meters. Coulombs cancelled, you're left with Newton meters. What unit is Newton meters the same as? Oh, come on, Newton meters. Think about the formula, which is a force multiplied by a distance. Yes, that is technically... No, something else, another one. Force multiplied distance. OM. The unit is work. Newton meters, also known as joules. J. See, it's responses like this that make me worry at night. Newton meters is the same as a joule. So the unit here, of course, is joules, as it should be. It's potential energy. Makes sense. This physics. Right, continue? Yes. Continue?
Emily King. The office of the international office officer. Her name is Emily King.
Right. The potential energy due to being an electric field is given by... Now before I go on, there is another way to write this formula. What is the formula for E between the plates? V over D. So this is Q V over D times D, which is QV.
Yeah, I was thinking because it's a D and it's a distance, can't we equate both of them and then to prove it?
Equate what exactly?
The PE and the MGH, the QED and the MGH.
Equate them?
Yeah.
No.
And then
No.
prove that it's
No.
the same.
No. Because this is true in space where there is no gravity. So the G would be 0. Okay. QV is another way to write this formula. So what you use depends on what you know for the question. However, writing as QV kind of reveals something interesting. That the only thing you need to know is the charge and the voltage of the plates. But that's not quite right, because you have to be careful here. Please be careful. This D is the distance it is from the plate, which, if it's the same as the distance between the plates, it will be this. But maybe just to be a little bit clearer,
D1, D2.
Yeah, if you had this one and then this one here. So the potential energy is QED, but this E, what's the form for E? V over D. And they only cancelled previously because I used the full length. But if it was in the middle, it wouldn't happen like this. So you can use this anytime, but you can only use this when it's at the top. Please be careful about that. Now in the exam, 99% of the time it's at the top anyways, so it doesn't really matter too much.
Not always.
Never 100% for anything.
So why can't we just use QED?
You can. I'm just saying as a shortcut you could use this. Because what would happen in the question, they wouldn't necessarily give you the E, you would have to work it out, so it's just a bit quicker. Okay, so the formula is QEH. And in this slide I've decided to use both a small and a big Q, just to keep it balanced, or QV. And I went back to H instead of D, so whatever you prefer. Okay. Remember, if potential energy is positive, what does that represent? What type of situation?
It is floating. It's above the ground.
Yeah, but more general than just with gravity.
It's stable.
No. If it has positive potential energy, then it has the ability to do work. There's energy stored in it and it's ready to do something. If the potential energy is zero, how do we describe the particle? Nearly, but different vocabulary, please. Not quite. No, not necessarily stationary. No, not necessarily stationary. No, it could be moving. It could be moving. If it's zero, we describe it as being free. And finally, if it's negative, do you remember what we describe it as? Say again? Close enough.
What?
Trapped. It's trapped. Meaning we have to give it energy to free it. For example, ionization energy. Electrons have negative potential energy when they're trapped in orbit around a proton. They require, as you know from chemistry, ionization energy to be freed. You've done ionization in chemistry, haven't you? Okay. You wrote this slide down in mechanics, but clearly you have forgotten it. Please rewrite it. Faisal, you forgot it too. Please rewrite it. That's my phone. I managed to get email notifications set up on it. 2 emails. Oh, IKEA. Did you all write that down? You all forgot it. Please asleep.
Oh, 24th June, prize party. 24th June, prize party. Drop dead twice. 3 p.m.
Could you explain what trapped in a potential well means?
Yeah, I suppose I should really say potential well is a synonym for trapped. So any physical problem where something is trapped, example, an electron around an atom, a planet around the sun, even like, if you have some kind of structure that's entangled with another structure, like 2 cars crushed together, you have to spend energy to free it. So we describe it as being trapped, But the problem is trapped is an informal term. So in physics we use a much fancier term and say it's in a potential well. Because we're imagining that the potential energy graph, like a well, dips down and you have to pump energy into it to get it back up. I'll read it later. Okay, you wrote that down? Continue. Okay. Now, you know conservation of energy. Energy can't be created or destroyed. So when we did it in mechanics, that meant the energy at the start equals the energy at the end. You don't have to write this down. I hope not anyways. You remember this from semester 1? Yes? Kinetic and potential at the start equals kinetic and potential at the end. You remember this, right? You haven't forgotten everything yet. Good.
Not only start and
Kinetic plus potential at one point in time must equal the kinetic and potential at a different point in time. Continue. This is true as well when we're looking at particles and fields. So for example, here's the particle here, and then it gets attracted to this plate here. It has kinetic energy, which is equal to a half mv squared. And what energy does it have up here? It has potential energy, which we said earlier was what formula? QED, or because it's at the top, QV. Now, because it's vertically moving, technically it also has potential energy from gravity. However, often we do not consider this because it is so small compared to this. So for example, this could be 10 to the whatever minus 5, whereas this one could be like 10 to the minus 10, for example, or whatever, because the mass is so small. So when you add them together, you don't really care about that because this is 10,000 times bigger. So for these problems, it is not usually necessary to consider the gravity potential energy. Anyways, there is a small problem, literally. When you use this formula, Q will be quite small. For example, what's the charge of an electron on your calculator? Actually, I've got it here. It's a constant 23, isn't it?
Electron?
Yeah, constant 23. 10 to the minus 19. The voltage would maybe be something like 10, 100, or 1,000. So even if it's 1,000, that's still a very small number. So we don't really use joules because joules is not the right size. The value will be really, really small. We use a different unit to measure energy here. Does anyone know a different unit to measure energy? And don't say anything stupid like microjoules or nanojoules, something else.
I was going to say nanojoules.
Not that either. Not even nanojoules.
Whoa.
No. Anyone know?
First letter?
E.
Electron volts.
Yes. But it doesn't work like that in the exam. The question is in what unit measures energy on the small scale? E. Blank, 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 blank. It doesn't go like that. Okay. So, because it's so small, we use a different unit. And that unit is called the electron volt. So, smarty pants, what's the definition of 1 electron volt of energy?
1 electron volt of energy is...
Yes.
Give me the first word.
No.
It is energy volt times 10 to the power negative 19.
No.
That's what it means, but like...
Any ideas? Well, I'll give you a clue. It involves 1 volt and 1 electron.
It is the voltage of 1 electron.
It's the what?
The voltage of 1 electron.
No. Electron volt of energy is the energy gained when one electron is accelerated by an electric field of voltage 1 volt. Before you write that down, let's just calculate what that means. I'll draw it here. So this here is 1 volt, and this here is 1 electron. And 1 electron volt is the energy this has. How much energy is that? Well, if we use our formula, what was our formula here? QV. Now that's nice for this definition because what's V?
1.
And Q is the number I have on my calculator, or at least I did have a moment ago. That was it, 1.6 times 10 to the minus 19 joules. So in other words, 1 electron volt is the same as 1.6 times 10 to the minus 19 joules. So electron volts are suitable when you have a small amount of energy on the scale of 10 to the minus 19. Okay, so that's just my explanation, but for the exam you need the definition I wrote a moment ago, which I'll go back to now. So this is an exam definition. I've seen it a couple of times. It's the type of definition that you should understand because it's not too complicated. Sound effects not required for the definition. Huh?
About times
What do you mean?
okay.
Yeah, we're getting there.
Going to the library and studying.
Oh, that.
Yeah. Not going to the library and sleeping.
Yeah. Don't worry, I'm sure you're not the first student or will be the last student to have done that.
Yeah, okay, I got this.
Continue. Lee, continue. Go on.
Is accelerated.
1 electron volt of energy is energy gain when 1 electron is accelerated. Should be D at the end. Let's see. Mistakes by Stephen. Yeah. Mistakes by Faisal. Whoa! This requires 2 hands to hold up. Right, continue. And there's a bit of a difference here. This grammar mistake would not cost me any marks in the exam.
But if I was writing and I wrote this, it would cost me 2 marks.
No. Continuing. Right. You all have that, yeah? Here is a very small question which I've already done. What is 1 electron volt converted into joules? 1.6 times 10 to the minus 19 joules. Already done it. Here's one for you to do now. Convert 1 joule into electron volts. Convert. It's not a trick question, it's a straightforward question. Yeah. Yeah. It should be a big number because electron volt is a small unit and joule is a big unit. So when you convert joules into electron volts, you should have many electron volts. Yes? Right. Here is one which you should be able to do because it's like a mechanics question. You have 2 plates. They're 2 centimeters apart, 500 volts. The electron leaves the negatively charged plate and accelerates towards the positive. How fast will it hit the positive plate? What should this remind you of from mechanics? What type of problem in mechanics is like this?
Straightforward.
Yeah, if I say, here's a particle 2 meters above the ground and I release it, how fast is it going when it hits the ground? In this problem, here are 2 plates. I release the electron from the top plate. How fast is it going when it hits the bottom plate? You do not need to consider gravity for this question because all the interesting stuff is happening because of the field, which is much stronger than gravity. So you can, you can ignore gravity for this.
QED.
Huh? I don't know, I have to work it out. 10 what? Meters per second?
No, Newton, no, nothing.
Dude, I just said how fast will it hit the plate?
Oh,
I want the velocity.
Wait, so we don't use G as 9.81?
Are you seriously asking me? Because I will come there and slap you.
You said don't use gravity.
Yes.
So we don't use it.
Yes.
So we only have the distance and the U.
Yeah. Guys, is this the sound of success, or?
what's the mass of an electron?
On your calculator was constant number 3.
That's the mass.
I think so.
Oh.
A really big number, like
Oh, I expect it to be quite a big number.
132625051.
Yeah. Yeah, because 500 volts is a lot for only 2 centimeters and for 1 electron. So that electron is really going to be accelerated towards the plate. Okay. Time to do it? Do you have an answer, Faisal? Lee, do you have an answer? Why not? You don't know what to do because you were asleep. Fawn, do you have an answer? Let's have a look. So, let's just write down the information that we have, as is normal. So we know the distance between the plates. What else do we know? The voltage. And we also know the charge and the mass because it's an electron. So let's have a look here. What did I say? 500 volts. And the distance is 2 centimeters. Yeah. And here is just a little old electron. And it will fire down and hit here. It has kinetic energy here. It had potential energy here. The kinetic energy at the end equals the potential energy at the beginning. So the V is equal to 2Q voltage over mass square root. So take out my trusty calculator. Square root fraction 2 times the charge of an electron, which of course is constant 23 on the calculator, times the voltage, all over the distance. All over the mass, which is constant number 3, isn't it? Now what's really interesting about this question is where in my formula did I use the distance? I didn't use it. The 2 centimeters is nowhere in this formula.
Yeah.
Which means if I change this question to 4 centimeters, it's still the same answer. And that's really important for the exam, because in the exam, often they don't give you the distance here. And sometimes students may think, oh, I don't have enough information. But,
Like someone you know?
yeah. But you don't need to know the distance, because in this formula we didn't use the distance. Why didn't we use the distance? Because we knew it began at the top. Yeah? And let me just get the answer out here. Is that? Which
1.3
13262 kilometers per second.
I wish I could know that fast.
So you're looking at 13,000 kilometers per second, basically. A huge number. Now, what was your question, Faisal?
Regardless of the distance,
Yeah.
the final velocity will stay the same.
Yeah.
So the acceleration is changing depending on the distance.
Yeah, it must do. So as you increase the distance, to keep the velocity at the end the same, the acceleration must decrease to sort of
Yeah.
match it.
Nice.
Yeah.
Is this caused by the field itself?
Yeah, because if you think about the electric field is V over D.
Yeah.
So as you increase the distance, you decrease the electric field strength. But remember, F equals QE. So by decreasing the electric field strength, you decrease the F. But remember, F equals MA. So by increasing the D, you're decreasing the A.
Yeah.
Yeah.
Wait, can we find the acceleration by equating mgh to QE?
Why not?
Yeah.
Because at the very beginning I said
No,
no gravity for this.
But,
No.
no, but then you said A is equal to G, so what if we replace G?
Oh yeah. You're making me
That's
sad
what
on
you
the
wrote.
inside.
That's what you
No,
wrote.
I didn't. You asked me this 10 minutes ago, and I said no. The importance of the word like here.
No, but you said
Yeah.
G is equal to A under the TE.
Correct.
Under the MGS.
Correct. Yes.
Yeah.
You're talking about earlier.
Yeah.
Do I still have that picture? Yeah. Oh, there. You're talking about here.
Yeah.
You are absolutely 100% correct. The A is equal to G. Correct. Now, what is your question?
So can we equate, since they're both equal to
No,
PE,
I said.
but then PE,
Is this the same as this?
no, but then PE is equal to PE, isn't it?
No. This is the potential energy, and I can write a little subscript here. Potential energy caused by gravity. This is potential energy caused by electric fields. So we can't say they're the same. No, I understand your confusion now. You are looking this as two formulas for PE. And you say, why can't we make them equal? Because they're both PE, right? But the problem is, which is maybe not clear from using the letters PE, is that with PE, this is the PE in a gravity, and this is PE in the electric field. So although they're the same letters, if it helps you, you can give them different subscripts, because you can't say one is equal to the other. Yes.
So the mass of E.
Yeah. Electron? Yeah. It's on your calculator. It's constant 3. Look. Shift 7 O3. Mass electron. Yeah? Okie dokie. Yeah, to the answer, yeah. Did you all write that down? Andrew? You wrote this down? Giving up on me? I'm not giving up on you. Yes? What's what? What's what? Forget about this. This is just me explaining something to Faisal. Okay. You have that? Yes? Yeah? I don't know if anyone knows this. Can you think of any devices that make use of this technology? Any device that uses two plates to accelerate an electron? So you think about this, this is very, very simple. You could make it at home.
Mass spectrometer.
Yes, very good. Mass spectrometer is one. Excellent. Anything else? Anything else that uses two plates with a voltage to accelerate an electron?
I've seen something like that that's reduced to light.
The thing is made from the metal to other.
Go on.
Like when they want the, for example, the gold go to the spoon, for example.
Oh yes, electroplating.
And the gold go to the spoon.
No.
No?
Well, I mean that's more complicated than this. I just mean things that just use two plates and an electron. No, I know what you're talking about. It's called electroplating. Yahya's example of the mass spectrometer was good. Any other ones?
Home?
At home, yeah. There's something in your home, old something in your home. An old CRT TV.
Oh, no one uses those anymore.
I know. So you know those old televisions, pre-flat screen? Yeah. And you see there's a little box at the back here. Electrons are being fired at the screen using two plates. Yeah. Does anyone know what the screen is made of? Yes, on the other side, where the magic happens. Phosphorus. Or some other material which is whatever it's called, luminous or something. When it's struck by an electron, it lights up. So, you want a picture on your TV of a man, then you fire the electrons at the place on the screen where you want the phosphorus to light.
I used to take out the
screen?
Yeah.
Nice.
And it's all shine, it's not have the main like that. It's all like light.
Yes, but you need to fire electrons on it to make the picture. See, the phosphorus will be black. Black. But then when you fire electrons on it, it changes colour.
No. But when I saw it, I put that out.
Yes.
Like in normal, it had the shape of everything. Like the man like that.
Yeah.
It's normal. But when I put out the screen.
Yeah. Was the power on?
Yeah, it's still on. And it's shiny.
And you could still see the man?
No, not the man.
Yeah, because the electrons aren't hitting the screen anymore.
So it's shy.
It should be bright.
Only the light.
Only the light, yes.
It's not as the man.
Yes. I don't know if that's a good idea though. You took this.
It's childhood. It's plain.
You took the screen out when the power was on.
Yeah.
Don't try that at home, okay, guys?
We don't have to do this.
Well, that's good, maybe.
That's already.
Yes. Yes.
But it's dangerous.
It is very dangerous.
Just a little bit.
Yeah.
You only must die.
Yeah.
But it's cool. It's like
No, it is. I'm not saying it's not cool, but it's still dangerous. Like Faisal said, you only might die. But Faisal, as you can see clearly, she is not.
She's alive.
She's alive today to tell this story. Right.
Maybe not fully functional.
Debatable.
But nothing happened. Like it's still like
Nothing
if
happened.
you put again,
Next time,
it still
next
has the main.
Don't try it a second
Next
time,
time,
okay?
next time you do it, try touching it. See what
No,
will
but
happen.
like put out nothing, only shine, and then put in it again the main.
Yeah, because what's happening, here's the top, okay? This is from the top. You're looking down, okay? You have the phosphorus screen here, and here is where the electrons come out. When you pull the screen out, the man should be gone, because no electrons are hitting the screen. When you put the screen back, the electrons hit the screen, and the man should appear.
No, not dangerous.
No, it is dangerous. It is still
Why
dangerous.
is dangerous?
Because it's electricity. Electricity is dangerous. That's why.
Cool.
Okay, go stick your finger in the
Wrong.
plug it in.
The most dangerous part is here, where the electrons come out. This is safe-ish.
Yeah.
From
Yeah, I
outside.
put that,
Yeah.
not the back.
Oh, good. Yes,
Yeah.
you pulled this out. Yes,
Yeah.
yes, yes. But this has phosphorus on it, and you know from chemistry, phosphorus is toxic. And also, if phosphorus is exposed to the air,
Phosphorus oxide.
what happens when phosphorus is left out in the room?
Oh.
Yeah, well, phosphorus, if it's left out to the air, it burns.
Yeah, combustion is really high
Yeah.
in phosphorus. Correct.
So, if you take this out and accidentally break the screen and phosphorus gets out, then you've got yourself a fire. Not any ordinary fire, you've got an electrical fire,
Whoa.
which means you cannot use water. Nice.
Wow.
Bet you
So
didn't know
lucky.
that one.
Quite
So
lucky.
lucky.
Quite lucky.
I hope.
Yes, indeed. Okay. So, here are some questions for you to try now. I'll put them up on the screen here, on the larger one perhaps. Okay, how do I... Great, okay, can you try these now, and we'll have a look at the answers in the next class. But you should get these finished before going home today. Yes. Try your very best.